Swayam Prabha. Digital India. Educated India.
Welcome back to the lectures on nuclear astrophysics. In the previous lecture, what I discussed, with that let me do a quick recap, then I will discuss some more points in today's lecture. So, what I discussed in the previous lecture? Main features of the HR diagram, Hertzsprung-Russell diagram. You have seen how the data obtained regarding the stars in terms of luminosity and temperatures have been plotted, and what are the important outcomes of this HR diagram? L is not constant, it varies from one star to another star. Okay? And we also have seen that most of the stars are grouped into a cluster called as main sequence. Okay? And brightest stars are supergiants, and we have seen why certain stars appear only in specific regions of the HR diagram. And one more thing which I missed in the previous lecture is any theoretical model of a star, is constructed by solving a set of 4 partial differential equations. Okay? If you want to construct theoretical model of a star, one need to solve 4 partial differential equations for radius, luminosity, pressure and temperature. Okay? Because these equations describe the structure of a star as a function of the distance from the center and also as a function of time. And the time sequence of such solutions of these equations represents an evolutionary track in HR diagram. Okay? And already I have told many times that energy is generated via nuclear reactions and gravitational contraction, and more I will discuss in detail in coming slides. And how energy is lost? The generation of energy is because of the nuclear reactions, and how these nuclear reactions are happening I will discuss in detail after some time in the same lecture. Okay? But how energy is lost from a star? One of the entities which takes away the energy by not depositing within the star is neutrino, because it is weakly interacting. And I have discussed in one of the previous lectures that it is the detection of neutrino which is useful tool as evidence of the nucleosynthesis in stars, because neutrinos are the byproducts of nuclear processes. So, the energy is produced because of the nuclear reactions, and how these nuclear reactions are happening? Because of the conversion of gravitational contraction into thermal pressure. Okay? When elements the nuclides they are coming close to each other because of the gravitational contraction, there will be a situation when this gravitational contraction leads to the creation of thermal pressure, and this thermal pressure initiates the nuclear reactions which further produce nuclear energy. And how the nuclear energy is lost? As I told, one of the important reason is the escape of neutrinos from the star. What are the other features I have discussed in the previous lecture as part of the features of the HR diagram? Okay. Not only neutrinos, but also sometimes gamma rays also can escape from the stars, and by detecting whom we have discussed about technetium 99 and aluminum 26, right. and the greater the total mass of the star, the greater is the temperature and pressure in the core of the star, and the faster energy is generated and a greater luminosity. This I will discuss in detail in today's lecture. Okay. And in stellar model, the modeling of a star, that means the stellar evolution model calculations, there are uncertainties. There are uncertainties due to incomplete knowledge of certain processes in stars, certain nuclear processes in stars, like mass loss, energy transport, rotation and magnetic fields. Okay. And remember that impact of this uncertainties associated with this nuclear physics on energy generation and nucleosynthesis is one of the important challenges in the complex puzzles in nuclear astrophysics. So, what I want to say is that if you consider the uncertainty in the calculation of energy produced from a star, the main reason is the uncertainty in the nuclear quantities, like energy levels, what are the spins and parities, nuclear reaction rates, nuclear cross sections, all those things I will discuss in detail. So, the point which I would like to highlight is following: the uncertainties in nuclear physics processes leads to the uncertainties in the estimation of energy produced from the stars, energy generation from the stars. There is error, because there is an error in the, there is an uncertainty in the quantities related to the nuclear physics. I hope this should be sufficient to have a feel about the significance of nuclear physics in understanding the stellar evolution. So, whenever you have been taught earlier in +2 or in BSc, if you have done the binding energy curve and simple concept of nuclear reaction, nuclear fission and Q value of a nuclear reaction, those are the values which are playing extremely important role in the calculation of energy generated from the stars, and the uncertainty is because of the uncertainties associated with the nuclear processes. So, this is all about the HR diagram and some more points regarding the HR diagram. Okay. And what are the points I am going to discuss in today's lecture, which I was supposed to discuss in previous lecture, that is mass and luminosity relation and some more selected general properties of the universe. So, let me see in this lecture how much I can cover. All right. See, in HR diagram, if you see what is the relation between mass and luminosity is not directly given there, right. What we have: magnitude, luminosity, temperature and a spectral color, right. These are quantities. But if I plot L by L sun and mass of the star by mass of the sun and see how it varies for all stars whose data is available, then you can see the location of sun here. Okay. And you see the scale, it is a logarithmic scale. Fine. Now, I mean it is a, this scale, if you take the logarithm value of L by L sun and this logarithm of m by m sun, okay, then also you will get a linear relation, and in this way of representation you can see the location of sun here. So, the luminosity and temperature, which I have discussed in previous lecture, they are changing at every moment due to their dependence on the mass of the star. Less mass, less luminosity most probably, and temperature also is changing. The mass is continuously changing. So, when you want to find out the change in luminosity and temperature, it is not constant for a star, it is not constant throughout the different timings. So, it is a strong, it strongly depends on the time, right, because the moment energy starts generating from the star, the chemical composition also is undergoing change. So, keeping this in mind, we can say that the most basic parameter which we have to consider is mass. So, that is how the mass and luminosity relation is important to understand, where you can see that it is a linear relation. Okay. And this studying the chemical composition and mass can be done by the studying the binary stars, two stars bounded because of the gravitational attraction. Okay. And this ML relation results from the fundamental laws governing the internal structure of the stars, because we are considering the variation in mass and chemical composition, which is further leading to the change in luminosity and temperature. Now, 90% stars, that means mainly main sequence stars, they obey this kind of relation. Now, this tentative number you have to remember. The luminosity of a star is proportional to the mass to the power of 3.5. Not for all stars, but yes, stars lying on main sequence, and the mass is varying with respect to the sun's mass, like 0.1 to 50, already I have discussed earlier, and L by L naught is ranging from -2 to -6 for these stars. Okay. And as I said, mass is one of the basic characteristics determining the evolution of a star. Large mass means you can easily expect burning rate is very high. So, when mass of a star is high, so there is a more material for undergoing burning. And what is this burning? Basically, it is the reaction between the nucleides, and this is caused by the thermal pressure, as I said. So, more mass, more burning, and quicker the mass of the star undergoing destruction. So, the lifetime of a heavier star in terms of mass will have less lifetime, because more mass, more burning processes, okay, more burning rate, and less lifetime of the star. And star, when it reaches to the final stage, dying stage, it may go to the giants or it may go to the white dwarfs, and that is part of HR diagram. Okay. So, this is some interesting diagram I have taken from this website, Hyperphysics. I think all of you are aware of this. Anticipated future of the sun. Right now, hydrogen burning is taking place at the center. Once it undergoes collapse because of the increase in temperature and kinetic energy, one can have faster fusion at intermediate radii, outward expansion in the outer region, and cooling at the surface, and then it becomes completely red, and it reaches to the red giant stage. Now, you might be having some idea the location of red giant star in HR diagram. Okay. And once it becomes red giant, the luminosity will be more because of the area, and mass will be very less compared to the original one, and this leads to the heating at the core to high energy like 10 to the power of 8 kelvins, and then helium will fuse to the carbon, and then flashes of helium will occur after a few years. Then the contraction, perhaps with some variability, will become white dwarf. So, this is some kind of anticipated future of the sun. In terms of diagram, we can see sun is here, and initially it will become red giant, and finally it will come to the white dwarf. What is this? So, this is nothing but HR diagram, right? Luminosity versus temperature or spectral color. So, this is the main sequence, one rough diagram, not exactly straight line, but you know the location of sun, it can go to red giant and then comes back to the white dwarf before it dies. So, this is some interesting diagram which explains the anticipated future of the sun, and all of you might be aware already sun has lost half of its age. Okay. It passed half of its tenure. Another property of the universe, Hubble's law. All of you might be aware of the essence of Hubble's law, so I will not take much time. So, why I am discussing this topic, Hubble's law? See, I have started discussing after optical astronomy and radio astronomy, all those astronomy techniques. I am putting in front of you salient features of the selected properties of universe. So, initially I discussed elemental abundance curve, and then I have discussed HR diagram, and as an extension of HR diagram, I have shown you mass luminosity relation. But remember, when you try to understand the HR diagram, please do not forget to do those numericals by taking different values of L by L sun and mass by mass sun. What will be the values of the size, that is radius, and density if masses are known, and from ML relation how to get the information about the luminosity if mass is known and vice versa. So, all these things please look into it carefully. Now, third general property which is very important is Hubble's law. So, what is the essence of Hubble's law? You are very well aware. So, quickly let me present some salient features of the Hubble's law which supports the concept of expansion of the universe. All right. So, this is a fundamental feature of the universe, Hubble's law. See, when you record the spectrum of a star, the wavelength of the spectral line shifts either towards red or blue, because with respect to the observer, the star is either moving away or towards the observer, right. With respect to the observer, the star is moving away or towards, coming towards the observer, and you know this is a well known Doppler shift. And what is this shift? Mathematically, this symbol is used Z, and wavelength in the laboratory frame and in the rest frame, when you consider the difference divided by the rest frame wavelength is nothing but the value of the shift delta lambda by lambda, and this Z in terms of velocity of light and velocity of the star with respect to which it is coming towards the observer or going away to the observer, okay, going away the observer. If you calculate the Z, it is more or less equal to V by C if this is the ratio is much less than 1. And when researchers have measured the spectra of stars light, and these stars are basically from all kinds of galaxies or clusters of galaxies, every spectrum has exhibited red shift, there is no blue shift. Okay. So, it is very clear that the expansion is taking place beyond any doubt, and the velocity with which it is moving away from the observer, that is recession, is happening with not slow rate, but in fact with fast rate. Okay. And this shift in the wavelength, that is red shift, is proportional to the distance between the source and the observer. Fine. Now, how to find out the velocity of the recession? Very simple, because it is proportional to the distance from the earth on which we are doing these measurements. There is a proportionality constant which is called as Hubble constant, Hubble constant, and at present the calculated value of the Hubble's constant is about 70 per kilometers per second, 70 kilometer per second, okay, and MPC inverse, where 1 MPC, okay, is equal to these many light years. Fine. And another interesting characteristic of the expansion is its nature of isotropic, okay, and this says that universe is more or less symmetrical. So, these are some of the salient features as part of Hubble's law, which is supporting the idea of expansion of the universe. So, this is one of the important selected property of the universe, and the progressive redshifts gives an idea about the expanding and isotropic universe. So, it is very important to analyze the redshifts in order to understand the isotropic nature of the universe and also expansion of the universe. Then after elemental abundance curve, HI diagram, as part of that I have also discussed ML relation and Hubble's law. Let me briefly discuss one of the most fascinating property of the universe, the detection of 2.7 kelvins radiation whose temperature is 2.7 kelvins. 2.7 kelvins. So, what are the salient features? Let me present in this slide. Okay. Like Hubble's law, it is also fundamental feature of the universe, and initially when Big Bang happened, there were huge temperatures, 10 billion degrees immediately after the Big Bang. Of course, slow cooling happened. All these things started around 14 billion years ago. Now, the detection of photons whose temperature, whose energy is corresponding to a temperature of 2.75 kelvins has been designated as most ancient signal ever detected. This is given as UBR, universal background radiation, universal background radiation, and the density of these photons of 2.75 Kelvin is about 430 photons per centimeter cube, 430 photons per centimeter cube. In 1948, actually Gamow, do you remember the contribution of Gamow? if you have been taught the alpha decay process, who proposed that it is the quantum mechanical tunneling process because of which alpha particle can come out of a nucleus. The same Gamow has predicted the existence of these photons of very less energy, which can give idea about the remnants of the Big Bang. Okay? I mean echo of the Big Bang, that is remnant of the 2.75 kelvins. Not only Gamow, some others also predicted the remains of this radiation. And the antenna in Bell laboratories, it found this cosmic microwave background, because it is in the region of microwaves, okay, because of which Nobel Prize in Physics was awarded to Penzias and Wilson. And this was the facility, beautiful diagram, photograph using this antenna, the detection of 2.75 kelvins was done, okay. And this is pervaded the whole universe, and this provides a strong supporting feature to the Big Bang. Remember, galaxies, that is a collection of stars, and quasars. What are quasars? Basically, they are the strong radio source. They are very much away from the Earth, beyond many galaxies, and quasars are also designated as the probes of the universe. So, beyond this I will not discuss, because I have to discuss the role of nuclear physics in the astrophysics. Okay? I hope you understand. So, for typical astrophysics concepts, you can go through another course, or you can go through many textbooks available in the market. So, the quasars, which are the strong radio sources, they emit microwave, but the intensity is different. Because when I say microwave radiation, that is cosmic microwave background, is assigned to the 2.75 kelvins, which comes into the region of microwaves. If you see the electromagnetic spectrum, this 2.75 Kelvin corresponds to the wavelength in microwave region. Quasars and galaxies, they also emit microwaves. So, why researchers are saying this 2.75 kelvins, they are coming from the distant away like 14 billion years ago, like that, because of the change in the intensity. So, it is not like the 2.75 kelvins in the microwave region, they are coming only from the, it is only the echo of the Big Bang. No, they are coming from different sides as well, but one has to look into the intensity as well. The intensity of the microwaves coming as an echo of the Big Bang is different from the intensity of the microwaves emitted by the quasars and galaxies. So, this clearly distinguishes the remnants of 2.7 Kelvin, which is the echo of Big Bang. So, interestingly, one can detect this radiation of 2.75 kelvins not from the galaxy or quasars, but from the echo of the Big Bang, as a part of echo of Big Bang, produced by this temperature as 1% of the background His television. Okay, more details you can find out in the internet. The His television, these antennas can catch this background. More details you can go through the internet. Okay. So, let me quickly summarize all these aspects of the astrophysics, which is basically trying to explain the universe. Okay. Observing the universe, it comes under the category of astronomy, and explaining universe comes under the category of astrophysics. Then I will start the role of nuclear physics. Okay. So, let me quickly summarize in a different way in these 2 slides. Fine. So, Gamow and his associates, they predicted the nucleosynthesis in the early universe. How? Because of the quantum tunneling process, even though energy is not sufficient for the fusion to happen, based on quantum mechanical tunneling, synthesis of nucleides can happen, and the expansion followed by the cooling of the universe to a temperature of 10 to the power of 9 kelvins. And basic idea of the nucleosynthesis is conversions of the neutrons into protons and then neutron capture reaction. This was the earlier idea, but later it has been proved to be incorrect. It is not the neutron capture reactions which are causing the formation of elements starting from hydrogen, after the hydrogen. Basically, they are the result of charged particle capture reactions, not the neutron capture reactions. Of course, I will discuss in detail in coming slides. Okay. And please do not forget to go through the papers of Cameron and B square FH, okay, Burbidge, Fowler and Hoyle. And what is the importance of Hoyle's work? I have discussed in one of the previous lectures, triple alpha reaction, right, which is the source of energy from red giants, isn't it? Anyway, so the articles whose first page I have shown you in one of the earlier slides, okay, they will help you in getting the papers of this B square FH and also the Cameroon. Fine? Okay, please ignore this folder, fine, yeah. And Hoyle and Taylor in 1964, they have found out the abundance of helium. That was the important milestone in astrophysics, okay. And then it comes out that it is clearly known that from the elemental abundance curve and the detection of gamma rays from aluminum 26 and technetium 99, that gamma rays are coming from the distant places. So, it is because of the nuclear reactions, right. And what kind of nuclear reactions are these? They are the thermonuclear reactions. They are the thermonuclear reactions, because these reactions are induced by the temperature caused by the surroundings. And who is contributing to this temperature production? The gravitational contraction which is happening continuously when nucleides are coming together. After a certain stage, they are the gravitational contraction is creating some kind of thermal pressure, and this thermal pressure is causing the nucleides to undergo nuclear reactions. That is the reason we call these nuclear reactions as thermonuclear reactions. Okay. So, the understanding of these thermonuclear reactions is very important to know the production of energy from the stars. Not only that, to understand the synthesis of elements in stars because of the nuclear reactions. Okay. So, what are the thermonuclear reactions, properties, all those things we will start discussing right now. So, from this I must say the actual part of the course has started, because nuclear physics, what is its role in the astrophysics, starts from the discussion on thermonuclear reactions, which are the key, which is the key to understand the production of energy from the stars and also the synthesis of elements in the stars. Fine. And as I said, initially when protons are formed, and because of the protons and neutrons fusion, when helium is formed, the condensation of this hydrogen and helium because of the gravitational energy. The gravitational energy which is causing the condensation, that means contraction of hydrogen and helium gas, is leading into the production of thermal energy, as I have said earlier. Okay? And this energy released in nuclear reactions, because this thermal energy is causing the nuclear reactions to take place, and the energy released from those nuclear reactions, energy released in those nuclear reactions, they stabilize the star for long time in general. Okay? The stability of the star is because of the energy released in nuclear stars. Okay? And exhaust of fuel, once the because of the chemical composition matter, because of the amount of chemical composition available, the exhaust of fuel happens, and then the contraction of stars happens again, converting the gravitational energy into thermal energy. And various stages are available, like first the hydrogen burning, then the burning of helium, and then burning of carbon, oxygen and neon, which leads to the production of elements whose mass numbers are between 16 and 28, and then burning of silicon, which causes the nucleides whose mass number is between 28 and 60, and after silicon burning you have more than 60 nucleides having mass number more than 60. They are because of three processes called as so-called S process, slow neutron capture, rapid neutron capture, and normally we can say proton capture. This is a very least role playing, but it has its own importance in understanding the nucleosynthesis. But coming to the energy production, S process and R process, they play very important role. And then there is one process called as L process, which is important to understand the production of reactive light elements like deuterium, lithium, beryllium and boron. So, students, in this lecture what I have discussed? ML relation, that is mass and luminosity, and mass of the star is proportional to the L to the power of 3.5 in case of stars lying on the main sequence, isn't it? Then I have discussed the other features like Hubble's law and remnants of 2.7 kelvins, that is the echo of Big Bang, and I have summarized the astrophysics which is trying to explain the universe. What are the important steps I have quickly summarized, and just I have started discussion on thermonuclear reactions. More properties about the thermonuclear reactions in the next lecture. Thank you very much for your attention. See you soon.